Here you can see that how this so this is the molecule. The breakage is possible between here. So if the breakage here over here, let's suppose the bond is being broken over here, what would happen? Well, the radical would one of the radical. So this homolytically cleavaged, and one of the radical has been left over here, and the other over here, and the charge has been generated because whenever this is bombarded, right, this is bombarded, one electron would be where has been electron been pushed. So you can see here that when this is cleaved homolytically, you can see here a positive charge would be created and here will be a radical cation generated. That will induce the radicalization in this bond, right, in this one. So this will also be being broken. So you can see that here is a double bond formation. So there is a loss of the ethylene because of this radicalization. And if this is homolytically cleavage, there will be a generation of the radical over here. You can see here. So you will be left with the positive charge in this carbon and the radical over here. Similarly, so this is what has happened. Okay, CC bond has been cleaved to produce the M radical, and then second fragmentation, second bond has also been cleaved. So two bonds are all together. They have been broken. Charge induced dissociation. You can see here what has happened. Firstly, the electron has been, firstly the electron has come to the molecule, and then this, the more susceptible, as I already told you, the most susceptible function in a molecule if you have the non-bonding electron or you have the pi electron. But here in this case we have pi electrons. That's why this pi bond has been broken and this has come from here, and then you are getting this cation and then this radical. And this radical now has initiated the fragmentation in the other. So this bond has been cleaved, right? So you have get this one. So this is radical induced dissociation, right? So you are getting this one. So it's very easy pattern. I think you can make a practice on, and then you will be having so many of such fragments. What about this one? Once this fragment is generated, this can go this way also. That uh, this can, been cleaved, and this can reach this can reach as a double bond to here, and you will be left a positive charge over here. So this has been cleaved here at these positions with the electron pair. So this is a charge induced dissociation. Why? Because there's already a charge over here. So that charge is inducing the dissociation of this double bond and it's moving up here, and you are be left with this cation. So whether that is the charge dissociation or that is the radical dissociation, both these processes are going parallel. So just sometimes it's possible that the sixth or there's a formation of a ring, and then the sixth or the fifth carbon can be abstracted. You will see this in the following examples. Here again, you see that as I said, that sometimes it's possible that if there's a formation of 5 or 6 membered, you can make that. You will not understand this slide unless you have not seen this one, this McLafferty. Just try to understand this McLafferty rearrangement, and then this thing will be easy for you to understand that why this charge has been shifted from here to here. Because this is a ring formation, and this ring is actually, this proton is actually being abstracted by this one. This has been neutralized, and there's a shifting of charge from here to here. You can understand this from the McLafferty rearrangement. Now I will take your time to understand this McLafferty rearrangement. What this McLafferty rearrangement, which is extremely important in the mass spectrometry when you are talking about the fragmentation pattern. Sometime you will see some of the unusual peaks in the mass spectra, and you will be it will be hard for you to make a concept about that why how you will justify those peaks. So actually that is the McLafferty rearrangement. What is McLafferty rearrangement? McLafferty rearrangement is the gamma proton shift. Why this is gamma? Because a gamma proton is being lost. How you will understand gamma proton? This is position number one. This is alpha. This is beta because it's a functional group. This is the alpha proton. This is beta and this is gamma. In the McLafferty rearrangement, a gamma proton is being lost and that is abstracted by this non-bonding oxygen electrons. So first of all, what happens that this McLafferty rearrangement is usually happens in the occur in the compounds with the carbonyl groups where the gamma hydrogen is being lost and abstracted by the oxygen. So how it happens? First of all, the electron bombardment happens on the occur on the oxygen, right? The non-bonding electrons they left, and then in the very next moment, what happens? The gamma proton is homolytically the bond with the gamma proton. They are homolytically cleaved and then abstracted by this oxygen radical, and then you get this OH, oxonium ion. And then what happens here? A radical is generated this position. Here is a radical. Now this radical, as you know, that this can induce the fragmentations. That is called the radical induced fragmentations. So radical induced, it can cleave this bond. So once it cleaves this bond, you will see that you will be left with this and this one. So whenever you get these peaks, you can understand that McLafferty rearrangement has happened. Just calculate these masses, these two. The relative abundance of this metal is 5%. And if this phenyl group, okay, they are saying that why the relative abundance of this McLafferty rearrangement would be 5% if we are trying methyl group over in place of this R, because in that particular case this radical ion would be least stable if we are having methyl group adjacent to this radical. That's why the relative abundance of this is 5%. But on the other side, if you have a phenyl ring over here that can stabilize this radical, in that particular case we would have 100% abundance because phenyl radical would be highly stabilized. This radical would be highly stabilized by the phenyl ring. So in that particular case, we will have 100% product, 100% peak for the McLafferty. That is the gamma proton lost. I think it is making sense. It's not a difficult thing. So these are some more examples. You can see the same McLafferty has happened, gamma proton. So they are explaining here that how this sometimes this ethylene ion formation and the adjacent O-methoxy group will be lost, and there's a possibility of the other one. So you will always go with the larger peaks. And here, if I consider the McLafferty, this is the normal case. This is the normal case if the normal loss has occurred. But this is the McLafferty lost. McLafferty loss means that the gamma proton shift to the oxygen. It's very far now. Now it's very far, but this gamma proton is shifting and reaching this position. And in this case, the cleavage would be around here. So this fragment will be lost. In that case, you will get these two fragments. So you can justify those peaks. That's why if you I think they have not given the relative abundance of the 74 peak. I expect that will be yes, you can see here because of the McLafferty. See, this is the most abundant peak. Why this is most abundant? Because this is highly stable peak. And this 74 is the characteristic of this McLafferty rearrangement, right? This one. Now this is also possible 169, which is another type of the fragmentation, but that is least in the abundance, which means that it is least stable. The most stable the fragment, the high would be its intensity. So you can just go on and then make a clever guess about the type of the loss, 14 loss, what does it mean? If there is a loss of 45, I have already provided the table, so you can see from there that which particular loss corresponds to what. Sometimes it happens that a four-centered cleavage occur. This is a four-centered cleavage. Four-centered cleavage. If you have this kind of the ion formation, it's possible that the this hydrogen reach to this position. So there is a bond formation between this one, and there is a cleavage of this one, and double bond formation over here. So sometimes this fragmentation is also very common in the mass spectrometry, where you get the four-centered fragmentation pattern. Four-centered. This is the pattern. This was the OH-CH3, and now this hydrogen has been abstracted from here to here, and you get this thing, four-centered. So I think you can see this. This is the type of the cleavage induced. Here cleavage, here is the cleavage. You can see this McLafferty. So four-centered again, four-centered cleavage. I don't understand that what is difficult in understanding all these things. It's all about practice. If you have good practice, you can understand all these things. There's a logical guess about all these spectra, right? You can calculate the number of ring or degree of unsaturation using that formula, and then you can gather information from here. You can use the McLafferty. So whenever you are looking at the spectra, just imagine that you have to look at all the possibilities. Let me explain in the other video.